Welcome back, everybody. Today is all about the Petersson inner product. So what's the definition? Let's take a subgroup of finite index gamma and SL2 of Z. Let's take F and G and S sub K of gamma, the space of weight K cusp forms for gamma, and let's set the inner product of F and G to be 1 over the volume of gamma V sub gamma times the integral over the modular curve X sub gamma, which we defined many videos ago, of F of Z G bar of Z times the imaginary part of Z to the K power relative to the measure d mu of Z. And d mu of Z here is the hyperbolic measure dx dy over y squared if Z in the upper half plane H is given by x plus iy. Yes, this hyperbolic measure is invariant under GL2 plus of R as an automorphism group of H, and so it's SL2Z invariant, so this actually makes sense. Okay, I mean, there are other things you have to check, though. So first of all, what's going on with this volume here? V sub gamma is the integral over the modular curve X sub gamma relative of 1 relative to the measure d mu of Z. This is called the volume of X sub gamma, and you have the relationship V sub gamma is the index in SL2Z of the subgroup plus or minus the identity times gamma. Okay, all of that index times the volume of SL2Z. Now, I mean, does this definition make sense? First of all, is the integrand even gamma invariant? Yes, it is. It's also bounded. Does the integral converge? Yeah, it converges absolutely. Okay, perfect. I mean, but the other thing is this actually an inner product? It's linear in F, it's conjugate linear in G, it's Hermitian symmetric, it's positive definite. But most importantly, you may have noticed this. If I take like a subgroup gamma prime in gamma, such that F and G are also in S sub K gamma prime, I better get the same inner product relative to gamma that I do relative to gamma prime. And that turns out to be true. So this inner product is closed under taking subgroups of gamma. And this is essentially because of the normalizing factor 1 over V sub gamma out front. What I mean by closed under, again, is if you take gamma prime as a subgroup of gamma, such that F and G are in S sub K of gamma prime, then it turns out that FG with respect to gamma is the same as FG with respect to gamma prime, no matter which gamma prime you pick. Okay, so see Dem in Sherman chapter 5 for all these facts. The upshot is we have a well-defined Hermitian inner product on S sub K gamma, and this is called the Petersson inner product. Okay, so here's a nice fact. Proposition 12. Let's take a Hecke eigenform F in S sub K of n chi, and let's let P be a prime that doesn't divide n. Then the Hecke operators T sub P and the diamond operators diamond of P have adjoints. The adjoint of T sub P, so T sub P star, is given by the inverse of diamond of P times TP, and the adjoint of diamond of P star, is given by the inverse of diamond of P on S sub Kn. And if lambda sub P is the eigenvalue of T sub P for F, then I can tell you what lambda sub P bar is. I can give you a relationship between lambda P and lambda P bar. Lambda P bar is just chi bar of P times lambda of P. And then most importantly, the operators T sub n and diamond of n are normal operators with respect to the Petersson inner product if the GCD of little n and big N is 1. So for proofs of all this, see CSS chapter 3 and Diamond and Sherman chapter 5. And as a corollary, S sub K of n, so we're going to specialize, well, we've been specializing, but just keep in mind we're specialized to the case here, essentially that gamma is gamma sub 1 of n. S sub K of n has an orthogonal basis of simultaneous T sub n and diamond of n eigenforms for little n, big N coprime. Okay, and the proof of this is essentially the above discussion combined with the spectral theorem from linear algebra. It's immediate. Now, it would be nice, though, if S sub K of n had an orthogonal basis of T sub n and diamond of n eigenforms for all n, not just those n that are coprime to the level big N. Okay. But this is only possible. You're only going to get this orthogonal basis for all n if you are working within a special subspace of S sub Kn, the space of so-called new forms. And so next video, we'll talk about the new forms. So thanks for watching, and I'll see you then.